fast surrogate for approximating steady flow simulations. I am Takashi Shimokawabe from the University of Tokyo. Computational fluid dynamics is an important application in the field of HPC. Since CFD applications are based on many computations on grid, meshes, or particles, it is well known that computational cost of CFD is relatively high and CFD applications require a lot of computational time. To solve this problem, we use deep neural networks, DNNs, to build a fast surrogate for approximating the large-scale steady flow simulations. Here is a basic idea of DNN prediction of the flow. First, we perform the CFD simulations in a traditional way to generate the training dataset. In our research, we use the lattice-Boltzmann method for these simulations. Once we have the dataset, we build a network architecture based on convolutional neural networks, CNNs, which is one of the representatives of DNNs, and we train it. After training, we can use the trained neural networks to predict CFD simulation results. CNNs may become faster simulator. In order to make the training datasets, we perform LBM simulations using the D2Q9 model with a Reynolds number of 100 on a grid of 1000 times 1000. The fluid flows along the x-axis. We placed random-sized cylinders at random locations. Since it is difficult to train models using large-size data, we clip data with a size of 256 times 128 from original data. We split about 6,000 data into training dataset and validation dataset. Here is a network architecture. The encoding part is shared by all dimensions, and the decoding part is different in each dimension. The encoding part consists of several convolution layers. The decoding part consists of several deconvolution layers. We use signed distance functions and boundary condition of velocity as inputs. Signed distance function is used to represent geometry including cylinders. This model provides velocity fields as output. In order to improve the accuracy, the model provides the information of the location of object as mask. Here is prediction result for single domain. The left side of figures are the CNN prediction of velocity fields. The middle figures show the LBM ground truth. The right side of figures are the difference between the CNN prediction and the LBM results. As shown in figures, our model will predict the LBM ground truth. In order to predict the result of large-size domain, we propose a prediction method using CNN with the boundary exchange. In this method, we decompose a large-size domain to multiple subdomains. We train a network model to predict single domain results and apply it to the decomposed subdomains to predict the simulation results in each subdomain. In order to maintain consistency between values in the subdomains, boundary exchange between neighbor subdomains is performed. CNN and boundary exchange are performed iteratively until values converge. Here is the prediction result for decomposed multiple domains. The left side of figures are the initial prediction by CNN with an initial unknown boundary condition. After CNN and boundary exchange between subdomains are performed iteratively, prediction values are converged to reach the final prediction. The right side of figures are the LVM ground truth. As shown in figures, although there is a little difference especially in the boundary regions, the developed method can accurately predict values in almost all computational domains. Here is a conclusion. We have developed a deep learning fast surrogate for steady flow simulations. The proposed method predicts the LBM result by using convolutional neural networks. In order to predict simulation results on large-size domain, we propose the method using CNNs with boundary exchange. In the future work, we will extend the proposed method to 3D CFD simulations. Thank you for watching.